Okay, let's get started. So today, use this. This lecture, we'll be talking about section 6.1, which is eigenvalues and eigenvectors. So before we talk about that, can we just review a little bit about determinants? Again, we are sticking with just n by n matrices, and one of the key facts about determinants is that a matrix A, an n by n matrix, A is invertible precisely when what can we say about the determinant? If a matrix is invertible, the determinant is not equal to 0, right? And if the determinant is equal to 0, then the matrix is not invertible. So you have a criterion for invertibility in terms of the determinant. And it turns out that for this section, 6.1, and the next section, 6.2, that is really the key fact that we need about the determinant. Okay, so that was just to review this fact because we're going to need it. So anyway, let's jump to eigenvalues and eigenvectors. So can I give the general definition? So let's say that you have an n by n matrix First I'll say what an eigenvector is. It's yellow. A vector in Rn is an eigenvector. So we say that we'll just use x. A vector x in Rn is an eigenvector of A if for some scalar lambda, A times x is equal to lambda times x. Okay, and x is a non-zero vector. That's important. So if you have a square matrix, a non-zero vector x is an eigenvector if ax equals lambda x for some scalar lambda. And that lambda is called an eigenvalue. This is like a German, I think eigen means same. So that's what the origin of eigenvector is. So basically, if A times x is parallel to x, then it's then x is an eigenvector. And why do we require that it's a non-zero vector? What's wrong with the zero vector? I think the issue is if you have the zero vector, right, A times that is just going to be the zero vector, and any lambda is going to work. So let's just look at some examples. Let's just say that you have the identity matrix. Oops. Well, can you think of a vector? I think I can think of lots of vectors where a times x is a scalar multiple of x, I think every vector, every non-zero vector x in R2 is an eigenvector, because a times x is going to equal x. So my lambda is going to be 1 with eigenvalue 1. And what happens in, oops, how do I scroll up? Jeez. Scroll up here. Let's, hold on. There we go. Sorry, I'm using a different app. Okay. Oh, geez. Every non-zero vector x in R2 is an eigenvector with eigenvalue 1. Right. Okay. Oh, you have to pinch it a little to move it up. Okay. And now what's the next example? Well, the identity matrix was just an example of a diagonal matrix. Can we just do an n by n diagonal matrix? Oh, why not just go to lambda n? So these lambda, that's a lambda. That's how it's pronounced. So lambda sub 1 through lambda sub n, and you have a diagonal matrix. Now these eigenvalues can be 0. 0 is a possibility for an eigenvalue. It's just that the 0 vector can't be an eigenvector. Okay, can you come up with a bunch of eigenvalues for A? What happens if I multiply by this vector x? What am I going to get? I think we're going to get this vector that's just lambda 1 x1, lambda 2 x2, all the way to lambda n xn. Right? So when is this, so here's ax. So when is this second vector going to be a scalar multiple of the first one? Well, lambda 1, can lambda 1 be an eigenvalue? Lambda 1 is an eigenvalue of A with eigenvector. Can you come up with a vector that's scaled by lambda 1? I think it'll be 1, 0. It's going to be 1 for the first component and 0s everywhere else. So that's just E1, right? And lambda 2 is an eigenvalue of A with eigenvector E2. So can I just change E, I think EI, well, let's just leave this where it is, E1. And in general, lambda I is an eigenvector eigenvalue, I'm just going to write it like this, just to save time. It's an eigenvalue of A with eigenvector EI. Right? Because if what does this matrix A do? When you have a diagonal matrix, this first scalar is going to scale this first vector is going to scale the first axis, right? It's like the x1 axis by a factor of lambda 1. And lambda 2 is going to scale the x2 axis by a factor of lambda 2, and so on until you get to lambda n. So that's what's going on here. Now, are there any other eigenvectors? Well, if you think about it, how about 5e1? Can I just write that down? If I have 5e1 so A times 5e1, that's going to be lambda 1 to lambda n times 5 and zeros everywhere else, right? And what am I going to get when I multiply? I'm going to get 5 lambda 1 to 0. So 5e1 is another eigenvector for lambda 1. Right? So if, in general, if E1 gets stretched by a factor of lambda, then 5E1 will also get stretched by a factor of lambda. In general, the whole line through E1 gets stretched by a factor of lambda. Right. So can I just write that down? In general, see what am I trying to say? The eigenvectors with eigenvalue lambda 1 is the whole line spanned by E1, is the span. Okay, I'm not loving this app because well, anyway, it's the span of E1. And that's going to be true for lambda 2 also. That eigenvectors with eigenvalue lambda 2 is the span of E2 and so on. So in general, for lambda I, the eigenvectors with eigenvalue lambda I is the span of EI. Okay. So let's just do a quick example with actual numbers. Okay. So for instance, if you have 2, 3, right? And when there's no entries, okay, so when I leave this blank, these are really zeros, right? So what does A do? What does A do to the plane? So here's the x-axis, here's the y-axis. This 2 means that the x-axis is going to be stretched by a factor of 2. So like E1 is going to go to 2E1, and negative E1 is going to go to negative 2E1, and so on. I should use this. So x-axis is stretched by a factor of 2, and the y-axis is stretched by a factor of 3. Right. Yeah, so let's use green. So this 3 means that this axis gets stretched. So 0, 1 is going to go to 0, 3. 0, negative 1 is going to go to 0, negative 3, and so on. Now what about a vector? So I've given vectors along the x-axis. Those are eigenvectors. And along the y-axis are also eigenvectors. What about something that's neither? Well, if I have 2, 0, 0, 3, and I multiply by xy, I get 2x, 3y. Now, if neither of these were 0, right, could 2x, 3y be a scalar multiple of xy? No, because the first number gets scaled by 2, and the second one gets scaled by 3. So there's no eigenvector. So it's not going to be parallel, right? So like if I had, if I took a vector like this, like 1, 1, it's going to go to 2, 3. It's going to go like somewhere up there. So it's not going to go to something that's parallel to the original vector. So if neither x nor y is 0, xy is not an eigenvector. Of A. So that's just a very basic example. And one thing I just realized is that I should have been more precise above. I was a bit sloppy because technically eigenvectors aren't the 0 vector, right? And so I should have I think one thing I could have been, to be super precise, the eigenvectors with eigenvalue lambda I is the span of ei except you take out the 0 vector. Okay, I'm not going to make a huge fuss over this, but technically speaking, right, an eigenvector doesn't have this, the 0 vector is not considered an eigenvector, and so to be more precise, I should really just like take out the origin, take out the 0 vector. But this isn't something I'm going to worry too much about, because one thing we'll talk about is that the set of eigenvectors, once you throw in the 0 vector, is a subspace of Rn. And we'll talk about that next time. Okay, I'm trying to keep these videos a bit short because if I make a long video, it takes a really long time to process. So I think I'm just going to stop and do some more examples and talk about the more general theory in another video. Okay.